Hi, nice to meet you. My name is Charlie Cappelletti. I'm a student and undergraduate researcher in the College of Engineering at the University of Michigan. I can almost guarantee that in the last 5 minutes, you checked this icon on your computer or phone. While most of us are familiar with the simple act of plugging in our battery-powered device, what's not so simply put is the mechanism which takes us from this to this. Don't worry, in our next few minutes together, I hope to peel back the curtain of mystery on batteries. Let's get started. Modern batteries are made up of 3 basic components: an electrically positive cathode, an electrically negative anode, and an ionically conductive medium in between called the electrolyte. When a battery is discharged, the anode undergoes a reaction in which metal ions are released through the electrolyte and electrons are released through an external circuit. This flow of electrons is referred to as a current, which allows us to power our devices. These electrons then recombine with their respective metal ions on the other side of the battery, and the process of discharge is complete. Yet, something is still missing in my explanation. What even motivates this process of discharge in the first place? I may have told you what, but I didn't tell you why. Don't worry, I have something that might help. Introducing... Oh, this isn't it. Gibbs free energy. Now I bet you're saying, Charlie, Gibbs free energy? That sounds great. I love free. Well, first of all, no energy is free. But this video is, so I'll tell you everything you need to know about this wonderfully powerful concept for batteries. Gibbs free energy can be defined broadly as the maximum available energy to do work in a system under conditions of constant temperature and pressure. It can be represented as 2 more specific processes, the first being cohesive energy. Don't worry, there won't be a test on any of this. Cohesive energy is effectively the strength of the metallic or covalent bonding that occurs between metal atoms, how tightly they hold on to each other. The second quantity is ionization energy in water. It's also my middle name. Ionization energy in water is how tightly atoms hold on to their electrons in the outer shell. It turns out that atoms don't really want to give up their electrons because they're usually very stable with them. And when they escape, the electrons exclaim, "I'm free." We haven't heard them say that, but we think that's what happens. And this is all occurring in solution because of the electrolyte, which is typically a liquid solution that I mentioned earlier in the battery. Let's try to apply this. The key idea to understand when applying Gibbs free energy is that when Gibbs free energy is negative between the products and reactants, then that reaction occurs spontaneously, or in other words, it's free. In this chemical reaction, if the Gibbs free energy of the products, which is comprised of the cohesion energy and ionization energy in water, minus the same quantities for the reactants, was negative, then this reaction occurs in the forward direction without any additional energy input from the outside world. It turns out that this chemical reaction represents a fundamental battery called a galvanic cell, which is one of the very first batteries used and ever studied. Really, it's that simple. We've reached the end of our lecture. If you stuck with me the whole way, congratulations, you're now an expert in battery basics. If you decide to take a power nap, that's alright too, because here's the take-home message. In order to achieve a more energy sustainable future, we need to find better ways to store and transmute that energy. That's what a battery does. By understanding concepts like these, we can not only build the next generation of batteries, but battery engineers too. Thanks for watching, and as always, go blue.